Okay, so we've talked before about relations, right? And we had this kind of funny way of describing relations on a set A by kind of specifying a subset of the Cartesian product of A with itself, so A cross A. So I would say A is related to B if the ordered pair AB is contained in that set, which is the relation, like the subset of A cross A. But, you know, we had different ones. You could get less than is a relation, less than or equal is a relation, greater than is a relation, but there's all kinds of relations actually. They show up all over the place. There's a very specific kind called equivalence relations, which are used to kind of generalize equality in some sense, is to say when are we going to consider two objects to be the same? And we want to consider two objects to be the same when they, you know, we really have the properties of equality. And I'm going to get down to what that is. So suppose A is a set. So by definition, so an equivalence relation on A, so it's going to be a type of relation. So an equivalence so what kind of object is it? It's a relation on A. So some subset of the Cartesian product of A with itself. It's a relation on A that is, and now it's going to have three properties that are going to kind of make it work like equality. So the first one we have, so I'm calling this ER for equivalence relation 1. So this is, it must be reflexive. Okay, so reflexive is that we have that A is related to A for all A and A, okay, which is the same thing as saying that, so i.e. AA is in the relation and every element is related to itself. Okay. So this is for all A and A, and every element is related to itself. And if you think about it for a moment, you can definitely think of relations for which this is not true. Okay, 1 is not less than 1. And there will be more examples like that in the next piece. Okay, so the next part is that it must be something called symmetric. Okay, so what does it mean for a relation to be symmetric? It means that for all A, B, and A, we're going to have that AB, so A is related to B if and only if B is related to A. Or you'd say, so AB implies BA, so A is related to B implies B is related to A for all A, B, and A. Okay, so i.e. AB implies BA for all A, B, and A. And another way to view that is if A is related to B, then B is related to A. Okay? And then there's one last property that we want equality to have. And again, this is something that fails for less than, because 1 is less than 2 does not imply that 2 is less than 1, right? So here's our last property. So each of these must hold, so I like to put a big and to indicate that. I think sometimes people list things without indicating whether they mean all of them are true or one of them must be true. So I try to always be specific about that. So here's the last property. The last property is it must be transitive, which is something that also holds for equality. Okay, and the way that transitivity works is that if A is less than B and B is less than C, or sorry, if A is related to B and B is related to C, then A is related to C for all A, B, C, and A. Okay, and I emphasize here, so I misspoke, but it's actually true that if A is less than B and B is less than C, then A is less than C. Okay, so that it is a transitive relation, even though it fails the other parts. I.e., this is not what I meant to say. I.e., so is in the relation implies that this is in the relation this is what I left a part of it. I could have written, if I told you what the relation was and called it S, I could have said AB and S implies B, A is an S. That was how that got a little crazy. Okay, so also there's a chair a little bit too close to where I'm lecturing for how absent-minded I tend to be. Okay, so if AB is in the relation and BC is in the relation, then AC is in the relation. Okay, so that's one way of looking at it. And another way of looking at it is to say, if A is related to B, B and B is related to C, then A is related to C. Okay? So this is if you have a relation, okay, so a subset of the Cartesian product of A with itself, and it satisfies reflexivity. Every element is related to itself. Symmetry, if A is related to B, then B is related to C. And transitivity, which is that if A is related to B and B is related to C, then A is related to C. So if a relation satisfies all three of those, then it's an equivalence relation. And this is often treated like a way of saying when objects in your set are equal, and then allows you to do things like form equivalence classes and so on.